Imagine the moment you lie down on the operating table. Within seconds, as if a switch has been flipped, you drift away from the world. Classical medicine explains this simply as a slowing of brain activity, but the truth may lie hidden within the secret world of your cells, at the subatomic level. Is consciousness merely a simple electrical signal between neurons, or is it a quantum dance occurring deep within the cells? Today, we explore one of science's most provocative theories, the quantum gate of consciousness and the mystery of microtubules. If you're ready, let's journey toward the deepest laws of the universe. Imagine the moment you lie down on the operating table. The clear liquid injected into your vein switches you off within seconds, as if someone flipped a button. Your heart keeps beating, your lungs keep breathing, some of your reflexes even continue to function, but you are no longer there. Then, when you open your eyes, hours have passed, yet it feels as though only a single blink of time has gone by. This experience doesn't quite align with classical neuroscience's explanations. Anesthetics don't completely shut down the brain's electrical activity. So what is the mechanism that can suspend consciousness so rapidly and so completely? The answer may be hidden in an invisible structure deep inside your brain cells. Microtubules, the cell skeleton, or something more. Inside every neuron, there are millions of tiny protein tubes called microtubules. These structures, roughly 25 nanometers in diameter, about 1/3000th the width of a human hair, were for decades regarded as nothing more than the cell skeletal system. Simple mechanical supports that give the cell its shape and keep it upright. But in the 1990s, two names shook this view to its core. Oxford University mathematician Roger Penrose and University of Arizona anesthesiologist Stuart Hameroff proposed that quantum physics operates inside microtubules, and that consciousness emerges from these quantum processes. This theory entered the literature under the name Orch-OR, orchestrated objective reduction. The scientific community's response was sharp, and for understandable reasons. The warm and wet brain objection. The most striking phenomena of quantum physics, superposition, entanglement, require extremely delicate conditions. Quantum computers in laboratories must operate near absolute zero, around -273 degrees Celsius, in completely isolated environments in order to preserve this fragility. The brain, however, is a chaotic environment at 37 degrees, where billions of molecules are in constant motion. The idea that quantum phenomena could survive undisturbed in this noisy, warm structure seemed openly at odds with physical intuition. It was like expecting polar penguins to survive in the Sahara. The decades that followed slowly but decisively dismantled this prejudice. The evidence began to speak. In 2007, a groundbreaking study on photosynthesis by Fleming and his team showed that energy transfer in green sulfur bacteria occurs through quantum coherence, and remarkably, this was happening at near-room temperature. Nature, 2007. This discovery seriously undermined the assumption that biological systems could not make use of quantum processes. In 2009, a team led by Dr. Anirban Bandyopadhyay from the Max Planck Institute directly observed quantum behaviors in isolated microtubules. The tubulin proteins making up the microtubules were reported to exhibit multiple structural states simultaneously, that is, they displayed the property of quantum superposition. This was one of the first serious experimental pieces of evidence supporting the Penrose-Hameroff theory. The order within crystalline water. So how do these delicate quantum states remain intact in the brain's chaotic environment? The answer lies in the water molecules inside the microtubules. Under normal conditions, water molecules move in a disorderly fashion like people running in every direction across a crowded plaza. But the cylindrical protein walls of microtubules lock the water molecules inside into a tight geometric order. This structure is described by scientists as biological crystalline water. This ordered arrangement serves two functions. It creates a shield that prevents quantum information from dissipating, and it provides a stable environment in which quantum processes can be sustained. Like a specialized protective casing around a sensitive instrument, even if a storm rages outside, the delicate quantum events within can continue undisturbed. Hameroff's team directly observed, under laboratory conditions, that anesthetic molecules bind to tubulin proteins and to the water inside microtubules. It was proposed that this binding suppresses the quantum activity of microtubules, and that this, in turn, is what extinguishes consciousness. Phosphorus atoms and quantum memory. In 2015, physicist Matthew Fisher from the University of California approached the subject from a different angle. Annals of Physics, 2015. According to Fisher's hypothesis, the nuclear spins of phosphorus atoms in neurons possess properties capable of storing quantum information even at body temperature. Phosphorus is an extraordinarily common element in brain metabolism, a fundamental component of the ATP molecule, DNA, and the cell membrane. If this theory is correct, then nature over millions of years of evolution may have already solved the quantum error correction problem that scientists today are still struggling to crack. The central problem, the binding problem. One question neuroscience has long been unable to answer is this: when you look at a rose, how do you experience its red color, its velvety texture, its sweet scent, and its connection to a particular memory all at once, as a single unified experience? The brain's visual, tactile, olfactory, and memory centers are physically separate from one another. Classical neural transmission cannot fully explain how this information is integrated so flawlessly within milliseconds. This problem is known in the literature as the binding problem. Orch-OR theory proposes that quantum entanglement between microtubules may be what takes on this integrating role. Particles that remain connected to one another regardless of physical distance. The phenomenon Einstein called spooky action at a distance could synchronize different regions of the brain instantaneously. This hypothesis has not yet been definitively proven, but the problem it is trying to explain has not been satisfactorily resolved by any other theory either. Where do we stand? To be honest, the Penrose-Hameroff theory remains controversial. Many neuroscientists and physicists continue to raise serious objections. We do not yet have definitive, reproducible experimental data proving that quantum coherence directly produces consciousness at the neuronal scale. But we do know this: that biological systems are capable of utilizing quantum processes is now a documented fact. Evidence that microtubules are not merely structural scaffolding continues to accumulate. That consciousness cannot be fully explained within the classical neuroscience framework is gaining acceptance in an ever wider circle. Right now, as you read these lines, approximately 86 billion neurons are at work inside your skull, millions of microtubules inside each one, millions of tubulin proteins vibrating inside each microtubule. We do not yet know exactly what these vibrations mean, but the place where what you lost and regained on that operating table that you touches the deepest laws of the universe may be precisely there. Give this video a thumbs up if you liked it, and make sure to subscribe for more. I'd love to hear your thoughts in the comments below. Let's talk. What topic should I cover next?